In this video, we'll develop time-dependent perturbation theory. We'll start with the time-dependent Hamiltonian, then the defining equations for the wave function, and finally we'll give a solution to those defining equations. Up to now, we've only solved problems which are typically quantum statics problems. But more interesting problems always involve transitions in energy as a function of time. One example of these would be a two-level system in the presence of an electromagnetic field where you can transfer from one state to the other by either absorption or emission of a photon. So let's imagine that we have a two-level unperturbed system with eigenfunctions psi A and psi B. The eigenvalue equation for psi A is H0, the unperturbed Hamiltonian applied to psi A, is equal to E sub A psi A. Similarly for B, the energy is E sub B. Psi A and psi B are both normalized, and they're orthogonal to each other. If we want to define any arbitrary state of the system, we can express it as a linear combination of psi A and psi B. That is, psi at time equals 0 is equal to Ca times psi A plus Cb times psi B, where normalization of psi of 0 forces the modulus squared of Ca plus the modulus squared of Cb to be equal to 1. Now we can write the state of the system at any time t by adding in the time dependence for each of the stationary states. So psi of t then is Ca psi A e to the minus I e sub A t over h bar plus Cb psi B e to the minus I e sub B t over h bar. When we add a time-dependent perturbation, h prime of t, then the expression for the system wave function is going to be still the same, except Ca and Cb now become functions of time. So we then can write the full time-dependent solution as psi of t is equal to Ca of t, psi A e to the minus I e sub A t over h bar, plus Cb of t, psi B e to the minus I e sub B t over h bar. So the time dependence is in the exponential as well as in the coefficients. If we want to describe a transition between state A and state B, we can write it like this. At initial time t equals 0, Ca is equal to 1, but Cb is equal to 0. At a later time t, Ca now is 0 and Cb is equal to 1. So this would describe the evolution of the system from state A to state B. The wave function we've described above must satisfy the time-dependent Schrödinger equation, which is given by h psi is equal to I h bar partial of psi with respect to t, where h is the total Hamiltonian, that is the unperturbed static Hamiltonian, plus the time-dependent perturbation, h prime of t. We now have these three equations which we can use to solve for Ca and Cb. The first thing we do is apply this wave function into the Schrödinger equation. So the first term was h0 applied to this first term gives us Ca h0 psi A and the time dependence e to the minus I e sub A t over h bar. And just as a note, I've dropped the Ca of t here for simplicity, but we have to remember it is time dependent. Then we have the same term with Cb, Cb h0 psi b e to the minus I e sub b t over h bar. And then we have the corresponding terms with h prime. That is Ca h prime psi A e to the minus I e sub A t over h bar, and similarly C sub B h prime psi B e to the minus I e sub B t over h bar. On the right side, we have to take the derivative of these two terms, and we get four terms out of that. The first one would be IH bar times the quantity from this IH bar, Ca dot, so the time derivative of Ca, psi A e to the minus I e sub A t over h bar. Similarly, we have Cb dot, psi B e to the minus I e sub B t over h bar. Then we have the derivative applied to the exponential. So it's Ca psi a times minus I e sub a over h bar times e to the minus I e sub a t over h bar, and then again Cb psi b times minus I e sub b over h bar e to the minus I e sub bt over h bar. Now if you look carefully at this, when you pull the IH bar into this bracket, this term here becomes Ca psi a e sub a times the exponential, and this one similarly Cb psi b e sub b times the exponential function. But those two terms are exactly the same terms as you would get when you apply h0 to psi a, because then you get e sub a psi a, and when you apply h0 to psi b, you get e sub b psi b. And so those four terms will cancel. You're now left with four terms. Two on the left side up here, and two on the right side. If we take the inner product of this whole equation with psi a, we have the first two terms on the left side will come out to be like Ca inner product of psi a h prime psi a times e to the minus I e sub a t over h bar. Then the same one applied to the second term is Cb psi a h prime psi b e to the minus I e sub bt over h bar. And on the right side, the only term that survives is the one with psi a, because the one with psi b, because of orthonormality, goes to 0. So we're left with IH bar Ca dot e to the minus I e sub a t over h bar. If we solve for Ca dot, we get Ca dot is equal to minus I over h bar, Ca h prime aa plus Cb h prime ab e to the minus I e sub b minus e sub a t over h bar. H prime aa is simply this matrix element here. H prime ab is just this matrix element here. Similarly, if we close the inner product with psi b, we get two terms again. Ca psi b h prime psi a times e to the minus I e sub a t over h bar. And then you have Cb psi b h prime psi b e to the minus I e sub bt over h bar. And now the term that survives is the one here in red with psi b. So we have IH bar Cb dot e to the minus I e sub bt over h bar. Again, we can solve for Cb dot. We get that Cb dot is minus I over h bar Cb h prime bb, which is this matrix element, plus Ca h prime ba, which is this matrix element, times e to the I e sub b minus e sub a t over h bar. So these are similar equations, except that here you have a negative exponential, here you have a positive exponential, so a phase shift of 180 degrees. So, for a time-dependent perturbing potential in a two-level system, we need to solve two equations, and these are the two equations we had before. This requires computing the matrix elements for H prime. That's HAA, HAB, H prime AB, H prime BB, and H prime BA. And the matrix looks like this. Now, in general, these would not be 0, but many times the diagonal terms are in fact 0. And so we're going to assume that the diagonal terms are 0 for the moment. And then we have equations for coefficients. Then if these are 0, then these two equations simplify because the first terms in each of them goes to 0. And so we have Ca dot is minus I over h bar h prime ab e to the minus I omega naught t over times Cb, and then Cb dot is equal to minus I over h bar h prime ba e to the I omega naught t Ca. So the derivative of Ca is related to Cb, the derivative of Cb is related to Ca, and the matrix elements. And you notice that these two matrix elements are just the two off-diagonal matrix elements, and omega naught is just given by EB minus EA over H bar. We're assuming that EB is bigger than EA, so this is a positive quantity. So we have these two equations plus the definition of omega naught. We now want to solve these. We're going to assume that this is a perturbation, so H prime is small, and the system will start out in the lower energy state, that is in Ca equals 1. So that means that Ca of t is equal to 1 at the beginning. And Cb of t is equal to 0 at the beginning, before you turn on the perturbing Hamiltonian. To zeroth order, the coefficients will remain in the same state forever. If there's no interaction, they will remain in the same state. For a first order correction, we want to apply the zeroth order coefficients to the time-dependent equation. So we take these coefficients and put them into the defining equations for the time derivatives. For example, CB0 goes in for CA dot, and CA of t, CA0 of t goes in for CB dot. And so that gives us two equations. The first one is CA is just going to be 0. CA1, the first order correction, is 0. Because CB is 0, this means that this term is just 0. But now we have something interesting here. We have CB dot is equal to minus I over H bar, H prime BA, e to the I omega naught t. Because CA dot of 1 is 0, then CA is equal to 1. For CB, we have this defining equation, which is a differential equation we can solve by direct integration. That means that CB1 is equal to minus I over H bar, integral from 0 to t, of H prime BA of t prime, e to the I omega naught t prime dt prime. So this will not be 0 any longer. It'll be something different than 0 because of this interaction term that we've integrated to time t. We can develop the second order correction in a similar way just by taking CB, the first order correction, plugging it into this equation here, and you get a revised version for CA dot, and the same thing for CB dot. And for CA dot, the second order correction is minus I over H bar, H prime BA, e to the minus I omega naught t, times the quantity minus I over H bar, times the integral from 0 to t of H prime BA, of t prime, e to the minus I omega naught t prime dt prime. And that means we can integrate this to get CA, the second order correction for CA. And so that will give you two integrals, one outside the other. For C, the second order correction to CB is just going to be equal to CB, the first order correction for CB. So you can see the first order correction for CB gives you one integral, and that remains the same as the second order correction. For CA, the first order correction remains the same, but the second order correction gives you two integrals. So we can now write the full second order solution, includes the zeroth order, first order, and second order terms. So for the full solution, we have CA of t is approximately equal to 1, because it starts at 1, minus 1 over h bar squared, integral from 0 to t of h prime BA, t prime, e to the minus I omega naught t prime. Then you have another integral in this integrand, which is the integral from 0 to t prime of h prime BA t double prime, e to the I omega naught t double prime dt double prime, and that all is integrated over dt prime. CB, to second order, starts at 0, so the first term is 0, and the zeroth order term is 0, and the first order term is this integral that we already calculated, which is minus I over h bar, integral from 0 to t, h prime ba t of t prime e to the minus I omega naught t prime dt prime. And the second order term doesn't change because this remains the same. So this iterative solution, you can continue it on for higher precision. And in general, the nth order solution has n factors of h prime, right? So the first order term for CB has 1 h prime. The second order correction for CA has 1 here and 1 here, has 2. Now, in principle, these two coefficients, the exact solutions for CA and CB, must be normalized. That is, the modulus squared of CA plus the modulus squared of CB is equal to 1. But the approximate coefficients are not going to be normalized. They are a little bit off, and they're off to order n in h prime. So we can see how this works for first order. For first order, the normalization becomes CA is 1 in first order, and CB is this integral in first order. So if we take CA squared plus CB squared, it's 1 squared plus the modulus squared of this integral here. And you can see that this is non-zero, and consequently this is not equal to 1. But it's off by order h prime, actually h prime squared in this case.